All right, thanks everyone for being here for this CGD seminar. It's my pleasure to introduce Iris de Vries, who will be speaking today about the importance of natural variability for present and future extreme precipitation risk. Iris is currently a postdoctoral scholar at MIT, where she is a member of a team developing climate emulators to better quantify future climate variability and extremes. She completed her PhD in 2024 at ETH, where she investigated forced changes in precipitation variability and extremes, supervised by Sebastian Sippel and Reto Knuti. Previously, Iris has collected many interesting degrees, I learned. She has in addition to her PhD in climate physics, she has a master's in oceanography and bachelor's in biomedicine and aerospace engineering. So I asked her about that at lunch. And Iris is also a committed road cyclist. She organized a big cycling club in Zurich and has already bagged like more big climbs in Boulder than I have in living here for years. So find her to talk science and join for a ride after the talk. And so thanks a lot and take it away.
I hope this is on now. Thanks, Nathan. Yeah, so I'd like to tell you about the importance of natural variability for precipitation extremes. It's a bit of a hobby horse of mine, so maybe I exaggerate the importance of variability, but then you can come and tell me after, and I'm happy to discuss. This is work that mostly I've done during my PhD. Some of it is from my current postdoc at MIT. And all these people, most of them are at ETH, and then Rafa and Paul at MIT were instrumental in all of the results that I'm going to show. So to give some mandatory motivation for why extreme precipitation is important, I think I don't have to spend a lot of time explaining that, but here I put some pictures of relatively recent, not most recent, but relatively recent events that were associated with extreme precipitation, record-breaking or record-shattering extreme precipitation in different regions of the world, and that also led to massive impacts. And there's reason to believe that climate change exacerbated the intensity of these events, and also, therefore, the impacts. And extreme precipitation is one of the natural hazards that has already led to most economic and also human damage as a natural disaster, and is also projected to increase strongly with climate change and therefore be a massive contributor to future and present climate damages. So to give a little bit of structure to this talk, I will try to outline different aspects of precipitation variability, mostly how precipitation variability drives the probabilities of unprecedented surprise events in a very sort of statistical sense. So most of the talk will be rather statistical, maybe a bit theoretical, on changing variability of the extreme precipitation distribution. And then afterwards, I would like to go a little bit into a more practical view, more impact-based view on how natural variability also plays a large role in shaping true, current, and future extreme event probabilities, and also our preparedness, like social preparedness to those kinds of events, and therefore the risk. So first, a little bit of background on extreme precipitation, which I'm sure most of you are aware of, but I wanted to just get everyone on the same page. So we expect precipitation to change because of Clausius-Clapeyron, first of all, which prescribes that with warming, the atmosphere can hold more water vapor by about 7% per Kelvin. So this is the thermodynamic effect. And if that would be the only thing, what we would expect is that every type of precipitation event would become 7% more extreme or more intense. We don't see that because there is also other things going on, of course, in the weather and in the climate, and it's mostly energy constraints that damp this increase in precipitation in a mean sense. So these plots, I'm going to use this. Yeah, these plots by Angie Pendergrass, who I think she actually published this when she was here, show that the mean precipitation change has a certain pattern of decreases in some regions and increases in many other regions. Mostly over land we see increases, but the total is about 2% per Kelvin, so not the 7% that the Clausius-Clapeyron relation predicts. And then for extreme precipitation change, we see a similar pattern, but we mostly see that the green-bluish regions that are the increasing regions are much larger than for the mean precipitation change. And that then leads to this plot, which shows that variability has to increase in all these regions where the extremes increase more than the mean, because the tail of the distribution shifts further, or for you guys, the tail of the distribution shifts further to the right than the mean. So this is a change that or difference that we see in total or mean precipitation changes versus the extreme precipitation changes, which means a widening of the daily precipitation distribution. But what I'm more interested in really is what happens when we are already in this extreme tail. So does this expansion or the widening of the distribution, does that also generalize, or does it propagate into the extremes distribution? So basically, could we say that moderate extremes increase less than extreme extremes? And I guess intuitively it makes sense that this is important for impacts, because if the most extreme events become more extreme faster, that also means that the most devastating events become worse at a higher rate. So this is another plot by Angie as well, that shows, mostly focused on the black line, that shows the multimodal mean of this percentage increase per Kelvin warming of rain, but again in a daily sense. So here we have a pretty extreme percentile, like a high percentile of daily precipitation, but it's not yet a 1 in 1,000 year event. It's more 1 in a 10,000 day event. So that's not super extreme in an extreme sense. So what I'm really curious about, and what I have focused on and will continue to focus on, is what happens once we go outside of this plot. When we go to even more intensities, like 1 in 1,000 year extremes, do we then see that this percentage increase with warming, does it increase even more? And do we get this explosion of the most extreme events just going infinitely more extreme? Does it taper off, and do we have an asymptote at this 7% Clausius-Clapeyron rate? Or does something else happen? Like I don't think we know. It's definitely going to be a pattern that differs per region, and I'm very fascinated by this problem, and most of my talk is also related to this. So that's for the background. Now a little bit of theory to sort of explain or set the stage for the framework that I'll mostly be talking about today. So in most of the results I'll show, I'm talking about generalized extreme value distributions fitted to extreme precipitation. And I think I'm sure that most of you have experience with these distributions. But just to give a little bit of background so that we all have a bit of an idea of what I'm talking about. So these GUVs are distributions that describe block maxima, meaning that most of the time I take the annual maximum or the seasonal maximum of precipitation, one day some precipitation, and I fit a distribution to these in a non-stationary manner so that climate change is represented. And this then tells me the probability of certain intensities of extremes. And these GEVs, they look in a very schematic sense, approximately like that. I left out the axis for ease. So on the x-axis, you would see the precipitation intensity, and on the y-axis, the probability. So this is a PDF of a generic GEV of extreme precipitation. And what I'm interested in now, and what I'll be talking about, is how do these distributions change in a changing climate? There are 3 parameters that describe this distribution: the location, which is kind of like the mean, the scale, which describes the width or the spread, and the shape parameter. And generally, we assume that the location parameter mu and the scale parameter sigma change with climate change, and xi, the shape parameter, we keep it constant because it's very uncertain and difficult to estimate to begin with. So there are several flavors of changes to this GEV that might happen in a changing climate, and I will just schematically show a few of them. The first one is just a shift in the location parameter mu, which would shift the whole distribution up by a constant physical unit amount. So that means that a moderate extreme would become more extreme by the same margin in millimeters as a more extreme extreme. And what this also would mean is that the distribution would actually shrink in terms of variability because the extremes become relatively less extreme than the moderate extremes. This is, if you see what I mean. This is actually what we mostly see for temperature, right? Like we see that temperature, we're not entirely sure, but generally a 30-degree event becomes more extreme by not necessarily the same fraction as a 15-degree event, but everything just sort of shifts up a certain amount of degrees. Yes. Then the other flavor where we have one parameter change is the scale parameter change, which is widening of the distribution. And so here you can see that more moderate extremes become maybe even less extreme or increase by a small margin, whereas the more extreme events increase by a larger margin. So this is widening of the distribution. And of course, what we expect in practice to happen is that both occur at the same time. And if they both occur in a proportional manner, so if both the location parameter and the scale parameter shift by the same relative amount, so say both shift by this 7% Clausius-Clapeyron rate, then every event intensity will increase by a different amount, but the rate will be the same. So every event intensity increases by 7%, which basically means a uniform, you could say the distribution remains the same and everything shifts up by the same rate. Now, the most interesting flavor of distribution changes, in my opinion, is this one, which is where the variability increase is relatively larger than the mean increase or the location increase. And when we see that the tail of the distribution, so the most extreme events, become more extreme at a faster rate or by a larger margin than the moderate extremes. And this would also mean that the most impactful events explode the fastest, basically. So one thing that all these distributions have in common is that the tail extends further to the right. No matter what change we have, we will see that the tail of these distributions extends further to the right. And the stronger the change in variability, the further this tail goes. And what that means, basically, is that we open up a range of new possibilities, so a large range of potential record-breaking events. And that brings me to the concept of record-breaking, which is what I've focused most on in my PhD. And so based on these sketches, you can already see that the variability plays a large role in opening up this whole range of new possibilities for record-breaking. A little more theory, just an equation that tells us what the record-breaking probability is at any time t, where x would be extreme precipitation. And at any time t, the probability that we break the record in a marginal sense, so averaged over many realizations, is equal to this equation, which shows that the PDF, so the current probability of a certain event intensity happening, is important, but also this product, which represents over all the previous time steps, the probability that we have not seen something more extreme than x. And we integrate that over all x's to arrive at the full probability. And this equation is important because it shows that variability actually has two effects on record-breaking probability. Because on the one hand, increasing variability increases the range of large x's with non-zero probability. So it increases the value of little f of x for large x's. But at the same time, if we have a lot of variability, it decreases this term over time, as it's less likely that we haven't seen an intense event already. So there's a bit of a trade-off there that changes also in time when it comes to the record-breaking response to changes in variability. So that's record-breaking, and then one event that is also very sensitive to variability is record shattering. So this is, some people have called it record smashing before. What this refers to is the event in which a record is broken by a non-zero margin defined by the user. Often one standard deviation is used. And these are, of course, relevant from an impacts point of view because they are so much more extreme than the previous record that they almost always catch society by surprise. And these three events that I showed at my first slide were all also reported to be record-shattering precipitation events that then led to these floods. The only difference in the equation for record shattering is that we add this non-zero margin C to the previous record. And so that comes in only in this term because it's only relevant in the present PDF, which then again sort of relates back to this variability having a large impact on record shattering because the probability that we see something much more extreme than what we have seen in history increases when we have this large variability increases in the extreme distribution. Yeah, this is the last theory slide, I promise, and then we'll go into some actual results. just to give you a little bit of an intuition of how this probability looks over time. So in a stationary climate, we would have a time series that maybe looks like this, and every now and then a record would occur. But as time progresses, the probability of records decreases because every time step it's less likely that the new event is more intense than anything we've seen before. So the baseline sort of reference record breaking probability with time decreases with this negative power law. And then in a changing climate, as I said, we can have variability increases, mean increases, or both. And what we then expect is a deviation from this solid line that either we decrease less quickly or we even see an increase in record shattering or record breaking probabilities. And so really the effect of climate change is best represented by looking at the difference between this reference probability and the current or the actual probability. Okay, some results. So in my PhD, I analyzed record shattering probabilities in extreme precipitation in this quantity that I called 5-year arcs 1 day. So that's the 5-year daily maximum precipitation, a quite extreme quantity in order for the GeV assumptions to hold better in a pretty high warming scenario, SSP 370. And before I go into the statistics of record breaking, I think it's maybe interesting, also given that many of you probably work with CSM, to see whether CSM actually represents these record shattering precipitation events well, because it's relatively low resolution. Generally, things are parametrized. So would we even see this range of variability in the model? We actually do. So this is a time series of both observations. The solid line are the observations for the region in which the European floods happened in 2021 of arcs 1 day. And you see some variability and then this large spike that was associated with the event. And then in the dashed line, you see for the same region, the most extreme member of the CSM2. That's a 100-member ensemble. So I picked the most extreme member for that region. And we see a similar range of variability and then this massive spike in 2077, by coincidence on my birthday in 2077, which looks like, okay, well, CSM2 actually does have this very large variability, even though it maybe doesn't resolve all the processes that are important for extreme precipitation. And now the question, of course, is, well, but what does it look like? Is it just some sort of weird outlier? Turns out it isn't. And I really want to emphasize, I just picked the most extreme member. I didn't look at analogs. I didn't try to find a similar event. I just picked the most extreme member in the ensemble. And then I looked at a few meteorological variables that matter for these kinds of events. In the top row, you see the observations for the European floods. And the bottom row is the CSM 2077 event. And you see precipitation, updraft, vertically integrated water vapor transport, and the pressure situation. And they're not exactly the same, but in my view, this is pretty striking how similar the structure is of the pressure and the Z500 and the SLP anomalies, and also how the water vapor transport that partly comes from the Atlantic, but then also has this anticyclone that picks up moisture from the Mediterranean, how those are present in both of these events, which tells me that, at least for this event, of course, I didn't analyze all the record shattering events in CSM2, but the fact that this is so similar did give me some confidence that actually relevant processes that are plausible are present in CSM2. So given this, I then started looking at the statistics of record shattering probabilities in this ensemble. And as I said, the best way to assess whether this probability changes is by looking at the record shattering probability with climate change relative to this reference rate that just declines as time progresses. And what I show you here is the maps of the probability ratio, as I say there, of shattering a record in 2100 with climate change versus without. And this is based on these GEVs fitted to the observation. So I also determined it for just counting records. Looks very similar, but the analytical solution gives a little bit more flexibility. So the first thing we see is that probability ratios are larger than 1 almost everywhere, which is maybe not surprising, but still pretty striking, because this is breaking a record by 1 historical standard deviation. So almost everywhere over land, this probability increases with climate change. Secondly, we see some seasonal differences, where actually an interesting one is that the northern hemisphere in local winter shows relatively high record shattering probabilities, which I initially found surprising, but it has something to do with the type of event that leads to rain in those seasons. And we also see just a general pattern of high rates in the tropics, where generally we would expect high extreme precipitation intensities to begin with. So this is the overall complete probability distribution change leads to these probability ratios. But of course, I said that I was going to tell you about the importance of variability. So what I did also was to separate the effects of these different distributional changes on the record shattering probabilities. So here in the top right, you still see the total maps. And then on the top row, you see what the map would look like if we only had a shift in the location parameter. So if we only had a mean shift in the GEV distribution. And the bottom row is what we would see if we only had a shift in the scale parameter. And visually, I would say, but as I said, maybe I'm biased because I like variability. I think the bottom row looks a little bit darker than the top row. Like, variability just plays a large role in shaping these record shattering probabilities, and with only a scale parameter change, we would already see a large increase in record shattering probabilities at the end of the century. And also here there's these pattern effects where we see that the winter local hemisphere is actually more of a mean shift effect, which, as I said, has to do with large-scale precipitation being the driver of extreme events in that season. Whereas in summer, we see that the mean effect is virtually 0 or maybe even negative here at the Iberian Peninsula. And any effect that we see in summer is due to variability, because convective events are much more sensitive to variability. So this is these maps, but I would also like to zoom in for a slightly more detailed look, zoom in on these 3 regions that I circled there in summer, and then, or Northern Hemispheric summer, and also on the pink region, so the same European region, but then in winter, in order to separate, to look at the time series of record shattering probability and see in more detail how the variability and the mean changes contribute. So if we zoom in on these 3 regions, I chose Europe for the European floods and then Lagos, because that's, as you can see, a very red region, and also there is this enormous, rapidly urbanizing region between Lagos and Abidjan where millions of people live. Probably there's a massive adaptation gap, so I feel like that's quite relevant from an impact point of view. And then Pakistan, where the 2022 floods happened. So if we look at these 3 regions, and now you focus on the blue lines, which are the analytical estimate of record shattering probability. Now it's not the ratio, but the absolute record shattering probability in those regions. The blue solid line shows the total, and then the dashed line shows the record shattering probability if we'd only had a change in variability. And for all 3 regions, the dashed line contributes most to the total, showing that this variability change is really the key driver of increases in record shattering probability in extreme precipitation in these regions. Whereas the mean also does have an effect. So the dotted line is the mean, and that also, at a bit of a delay, it also starts to contribute in all 3 regions.
Is that 10% per year?
Yeah.
Yeah, okay. So every year you have a 1 in 10 chance of shattering a record?
Yeah, so this is...
Up to 20?
Yeah, so this is the 5-year ARCS-1 day. So that means any given 5-year period, you have a chance of 10% of shattering the 5-year record. Okay. Yeah.
Percent per 5 years.
Yeah. Which, I mean, also it really depends also on the length of the time series, right? Because you decline with time. Yeah. And so given that it starts in 1850, you don't have that much time to spin up with 5-year blocks. But here in Lagos, it reaches 50%, which is pretty nuts, right? Like 1 in 2 chance every 5 years in a high warming scenario. I have to give that disclaimer. Yeah, as I said, it's not always about variability. So here in winter in the European region, we actually see that the dotted line, so the mean change in the extremes distribution, contributes more, as I said, because of the type of event that causes rain in this season. Right, so now I guess a question that might arise is why, even though maybe I've already made it quite clear, but why is variability so potent in increasing these record-shattering or record-breaking probabilities? And as I highlighted already, it's really because of the effect of the sigma changes versus the mu changes on the GeV distribution. So if the sigma increase is larger than the mu increase, what we see is that events that are further towards the extremes, further in the tail, increase by a larger fraction, and therefore also that the potential for an event or a record to be shattered by a large margin increases as well. And I've been calling this scaling of intensification with extremeness, which is kind of a weird, it's just a lot of words to say. So my supervisor at MIT was like, we need to come up with an acronym for this. So we've coined this the Rareness Amplified Intensification of Extremes effect, also RAINY, which is quite a convenient acronym. And this is really what I'm working on now. So this is all sort of unfinished and very much work in progress. But this RAINY effect is something that I'm very interested in, and I think is very relevant to better constrain whether this is actually true, and if so, like where does this happen? Where is this the strongest? How do models project this? But also, can we see this in observations? Can we constrain model uncertainty with observations? I think this is a very interesting aspect of future extreme precipitation. And if you can bear with me for a little bit more theory, I would like to show a few equations, because it's actually really elegant, and I was happy to find that there is such a simple way of explaining how we could diagnose whether the RAINY effect is happening or not. So this equation is just the CDF, so the cumulative distribution function of a GeV is e to the power tx, and tx depends on mu, sigma, and xi, as I said before. And x here is, say, rx1 day, or some extreme precipitation quantity. But now what we want to know is not f of x, but we want to know whether the change in x depends on f, because f is the quantile level or the percentile of x. So we want to know, does x rain change more if the quantile level is the 99th percentile versus if it's, say, the 80th? So if we rewrite this as a function of x, then we get this function that's dependent on f, so on the quantile level, and then we determine the relative change in x. So this will be dx divided by x, which is then also a function of the quantile level, which is what we want to know. And then this is really the form that I think is, well, it doesn't look very elegant, but that is very simple and gives us a clue as to what matters. So the relative change in x in rain depends on the relative change in mu, and then something like some function of f that's dependent on the difference between the relative change in sigma and the relative change in mu. So this term really just simply the difference between how much the sigma change relative to its starting value minus how much the mu change relative to its starting value, that determines whether we see an increase with extremeness or a decrease. That's shown in this very schematic plot. So here as a function of f of x, so that's the extremeness of the event, we see that if, in the red line, if we only have a change in the location parameter, so in mu, we see that the relative change in x on the y-axis decreases with f. So as we go to more extreme values, the relative increase actually gets smaller, which makes sense if you think about the distribution just shifting. And so the percentage increase for the most extreme events is smaller than for the more moderate events. If we see only an increase in scale, we get the blue line. So then we see this very strong dependency on, or positive dependency on, the extremeness, and a fast increase in intensification as we get to more extreme events. If we see that both increase by exactly the same fraction, we get just a horizontal line. So then we're independent of quantile and everything shifts by the same percentage. So it's really this difference between sigma and mu change that determines which way I flip. Do I get a positive increase with f or a negative increase rate? And Now I've been focusing on this quantity, like d sigma r, d mu r, and trying to better understand how that changes and if we can use that to project future changes or current changes in extreme precipitation. So these are very, very preliminary results on the native grid, Fred, in the Mesa Lab data, just to give you some intuition for this effect of mu versus sigma changes. So here I show you, it's basically the same as Angie's plots, but then for the extreme distribution. Here I show you the median change in RX1 day, and this is the change in the 99th percentile of RX1 day. And as you can see, the patterns are quite similar, but there's more blue in the 99th percentile increase, which is better visible if we subtract the two. So here you see the difference between the 99th increase and the median increase. And wherever it's blue, it means that this 1 in 100-year event intensity increases relatively more than the mean RX1 day, so the 50th percentile RX1 day. And then if we look at this d sigma r minus d mu r quantity, we see this. So, I mean, it's not very surprising because it's all based on the GeV, but it is striking that this quantity has exactly the same pattern as the intensification, and so sort of shows that this can be a proxy for analyzing where do we expect such an amplification of the most extreme extremes, and potentially also understanding why those regions have that whereas others don't. As I said, I don't have any answers yet. I'm currently looking into this. This is just for CSM1. I looked at it in some other CMIP6 models, which show a quite different pattern, so there's a lot of model uncertainty. I'm trying to figure out what can explain this. If you have any thoughts or ideas or questions, then I'd be super interested to hear that. So this is definitely a work in progress. Okay, that was most of the statistics. Now I would like to sort of change gears or shift gears a little bit and look more at an impact relevant or an actionable view on extreme precipitation and variability of extreme precipitation, namely real-world disaster risk. It's still about precipitation variability, but I would say it's a different view or a different angle to it. Whereas previously, what I've been talking about is how these mean distributions become wider. So how does the smooth trend in variability look? But for real-world disaster risk, I'd argue that maybe what's more important, or at least as important, is just the random fluctuations in our real observed climate. So natural variability in history. And I will show you why I think that's maybe more important. It's because variability can, especially for precipitation, mask the truth for decades. This plot by my former PhD colleague, Joel Tated, from Zurich, shows how for a pre-industrial, very long model run, RX1 day, so annual maximum precipitation, can have very different distributions for periods as long as 100 years. So this blue period would be the length of maybe our observations, right? Like 100 years approximately. Not even in every location we don't have 100 years. And if this would be our observational period, we would estimate that this level is our 100-year return level, the horizontal blue line. Whereas if we would live in this red period, we would estimate that this is our 100-year return level. And both of them are basically equally correct, you could say. And there's no way of knowing what is the actual 100-year return level, given that we don't have the observations of all the other arguable, same climate years. And so the truth can be masked or modified a lot by the natural variability of scales of our observational record, on time scales of our observational record length. So this then brings me to sort of a framework for analyzing real-world disaster risk or precipitation disaster risk, which is based on a few assumptions or a few hypotheses, really. The first one is that I think it's evident, but I've had to explain this many times. So I would say we have to assume that record-breaking and record-shattering events are likely to lead to impacts because they are unprecedented. So also the impacts are unpredictable, and so these are relevant types of events to look at for impacts. And more importantly, local record breaking can also occur at very low return levels because of this property of natural variability masking the truth or masking the true distribution. So where often for extremes, we maybe look at a 100-year return level or the changing probability of the historical 100-year return level, I'd argue that sometimes we might want to look at a 30-year return level because it might be true that we just haven't seen anything more extreme than that. And then looking at the 100-year return level would sort of ignore a lot of less intense events that could also be devastating for that region. And then the last part is a little bit less statistical and less natural science-y. It's about the social aspect of natural variability. So local disaster preparedness is correlated with historical disaster experience, meaning that whether a region has seen recent disasters or recent record-breaking events is going to shape how prepared it is and how aware it is of the probability of such events. And so taken together, this leads to my statement that local disaster risk is conditional on historical variability and should also be viewed or determined as something conditional on historical variability. And I will now sort of in separate ways explain how, both from a statistical point of view, just in terms of record-breaking probabilities, and also a social point of view, how this historical natural variability matters. So first, conditional record-breaking probabilities. I think it's quite evident what I mean when I say that, but I want to give an example based on a random 40-member model, RX1 day, according to that model in Switzerland. And if up to now, I've been talking about marginal record-breaking probability. So if we look at these, what we do is we count the number of members that breaks a record in any given year, and that gives us the average probability of record breaking in a marginal sense, but it doesn't tell us anything about what in our real climate, say in one member, would happen, because in one member, like how our observations look, we just have a few records scattered around, and these records are unaware of what the hypothetical total ensemble would do. We don't have an ensemble of observations. So when I say conditional record-breaking probability, what I mean really is that the only thing we use to determine our current record-breaking probability is the last record that we have seen. So say that we live here in the present, we have seen this record, and that record tells us what is our standing record and what is the probability that we break that, dependent on the distribution of current RX1 day. So this is a different view than these marginal probabilities. And to illustrate that in one other way, we go back to these record-breaking probability metrics where you've seen this plot before, or the sketch where record-breaking probability decreases with time in a very smooth manner, in a marginal manner. But when we look at the conditional one, we see a similar tendency. So it also will decrease in time, but because we update every time we see an actual record in our true local historical observations, we see that at any point in time, we are potentially quite far away from this marginal probability because it's this step function. So I'd argue that this conditional record-breaking probability that takes into account what is locally our standing record is much more experience-centric and potentially more actionable, more relevant from a practical point of view. And it's also very easy to determine because it's, as long as we know the local probability, it's just the exceedance of the absolute level of the historical record. So for any location, here I took a location in Africa as an example, we can determine based on observations, these are HEDX3 observations for that location, we can determine what is the current record up to the end of our observations, and we can assign a probability to that in the year it happens, and then we can extrapolate it forward in time with, say, climate models that tell us what the RX1 day distribution is in South Ghana with climate change. And this gives us the conditional record-breaking probability in any year in a changing climate. And when we do that for observations, this is again HEDX3 for all the locations for which we have an RX1 day record. then we see that the conditional record-breaking probability actually looks very noisy, and that's exactly the point. The natural variability of the historical observations in every location can really make the difference between a near zero probability of breaking the record by 2050 or a probability of 1. And there is an effective climate change here, but it's, as you can see based on the noise in this plot, that's actually relatively small compared to the impact of natural variability on true local record-breaking probabilities. And another reason why the local record is important, or the historical record quantile is important, is because these lines, sorry, I forgot the legend, but these lines are for 3 different observational data sets. You can see how the non-stationary probability ratio of shattering a record by 2050 depends on the quantile. And if you follow the solid lines, that's the conditional probability. You see that the higher the record quantile, also the stronger the increases in record-breaking probabilities with climate change. So both from a current risk point of view, it's important to know what is the actual standing record, but also from a climate change point of view, it matters what the current standing record is. Then the last part, that's the non-natural science part. That's the social effects of variability on preparedness for disaster. This is an example again from the European floods, where you see on the left the observed RX1 day time series in the basin on the right. And as you can see, for about 90 years prior to the European floods, RX1 day had been relatively constant. There are some spikes, but there is nothing massive until this event in 2021. And this is anecdotal or intuitive, but I would say it's quite reasonable to think that if 3 generations had not seen anything nearly as extreme as what happened in 2021, they probably were not aware of the fact that something that extreme was possible. And even if they were aware of that, they had very little experience and systems in place in order to resist such an event, just because 3 generations had not seen it. So this sort of goes into theories of frequency and availability bias and disaster memory, and that those affect how prepared or how aware a society is of the risk that they are exposed to, and also how well adapted they are to those risks. So I use this relatively, I would say there's a lot of aspects to this, and it's very complicated in a social sense, but I try to sort of simplify it down to do something quantitative with it. And again, here you see these time series in South Ghana, and I defined this quantity that I call the state likelihood, which is dependent on the historical observations in every location, and just determines how likely is it that we saw the record that we saw and didn't break it until the present, which is the truth, right? We didn't break the standing record, and you can compute over time how probable it is that in fact you didn't break the record. And this probability is then related to both the actual record-breaking probability, but also to how prepared society would be to an event. And I wanted to sort of validate whether this was reasonable at all in an anecdotal sense. So I took the HEDX3 observations again and determined this state likelihood in 2010, or I think 2009. And then I had another 5 years of observations to see whether record-breaking events in those 5 years after the year where I determined the state likelihood actually led to disaster. So that's what I show here. In this map, you see the state likelihood in every location in 2009. And so the darker the color, the less likely their current state is, meaning the less prepared they probably are for what might be coming. So they have a low record, and also they haven't seen anything extreme in a long time. So that's the dark regions. Then the blue frames are regions or grid cells where the record was broken in the 5 years following the assessment of the state likelihood. And the first thing that I don't show very clearly here, but that is true, is that there's more blue frames where the state likelihood is low, which is just a statistical property of a low record being more likely to be broken. But also I circled a few, or framed a few regions where we saw a low state likelihood and also a record being broken. And I couldn't do like a full, I would say, statistically sound analysis of whether there is a significant relationship between a low state likelihood and a disaster. But I did a simple Google search with like region, year of record event, and disaster. And for all of the regions that I framed here, there were a lot of hits and well-defined disasters that happened and that were associated with the record-breaking event that I found in the observations. Whereas for random combinations of just random combinations, I didn't find anything. And also for combinations of blue cells without a low state likelihood, there was a much lower like internet account of actual disasters having happened. And I just want to outline two that I found interesting. This is Irene. So in 2011, there was record breaking along the East Coast there in the US. And that was associated with Irene. So I sort of looking into the observations more closely, I found that the date of the record breaking in HEDEX 3 was the same as when Irene hit the East Coast. And looking at more sort of coverage, what you can see is that basically what I argue is you could tell from the state likelihood that there was a probability that something bad would happen there and that it would also lead to disaster. And yet you find these accounts of worst flooding in a century. Well, this is, yeah, it probably was the worst flooding in a century. And regions being completely unprepared for the event that happened, even though arguably it was predictable that something like that would happen. And I think this one is an even better example. So in Queensland in 2011, in their local winter, there was widespread flooding, and you also see that there it's very dark, so very low preparedness. And a 300-page report was written about these events in Queensland, where this quote I found quite striking. It says, "The disastrous floods were unprecedented, completely unexpected, and no government could be expected to have the capacity to respond." And I don't want to say told you so, but the completely unexpected, it does make me think, well, maybe we could improve the way we estimate and communicate these types of disaster or risk estimates to make sure that the next time it's not completely unexpected, because in some cases it might actually not be, and we can also integrate the social aspects to better understand where is the risk of disaster high and not just the probability of extremes. Yeah, so that's sort of the summary of my disaster potential framework, is to integrate state likelihood and future record-breaking probability to some sort of aggregate measure of disaster potential for extreme precipitation. Okay, conclusion. So I hope that, I think I said the word variability many times. I hope that I sort of conveyed that natural variability, both natural but also forced variability, is important for present and future extreme precipitation risk, because it increases the possibility of seeing unprecedented events and is very potent at increasing this probability. There's this rainy effect that I think is quite important to understand, to know which regions are most at risk for these strong increases in the most extreme events. And then I think to arrive at better, more useful, maybe more actionable estimates of disaster risk related to extreme precipitation, we need to take into account historical natural variability to both determine the current record and the record-breaking probability, as well as social effects of disaster memory and risk perception on, for future extreme precipitation risk. Exactly. So in the future, I will try to improve those conditional risk estimates and integrate the social aspects in a more satisfactory manner. Thanks.
I'm wondering how completely this characterization of extremes in the relative sense could map onto potential impacts. Just imagining maybe you have some location where you get, I don't know, like a meter of rainfall per day, plus or minus 1 millimeter. It's pathological, but in that sense, a 5 millimeter excursion would be a 5 sigma event, and yet the impacts might be relatively small. So are there locations where thinking about absolute impacts Or maybe this kind of record shattering that's a function of the mean could also be, another skillful indicator of impacts.
Yes. I understand your point. I think the record shattering I've looked at is always relative, so it's the local standard deviation that determines the record shattering margin, so that differs per location.
Mm-hmm.
Which means that at least, I would say that generally the idea is that the local variability is an indicator of what a locality expects, right? Like what they are adapted to, and as soon as you reach outside of that local variability, you will enter a region of unknown consequences, basically. Although I agree with you that sometimes maybe variability just is very, very small, and so still this increase doesn't matter much. I also think that when that is the case, you will see that the mean shift actually impacts record breaking much more than the variability shift. But I think I haven't looked at it in a complete sense, but I think it does sound relevant to look at record margins and relate them to both the variability but also to the mean in a more complete sense, yeah. Mm-hmm.
So I was just wondering, you in your statistical analysis, you are lumping everything together in terms of extreme precipitation, whether it comes from reanalysis, observations, well, you didn't use high-res, but low-res simulations. And I'm just wondering, you did not touch upon mechanisms or phenomenon associated with the extreme events. They can be associated with jets in France. They can be associated with, you could break it down, thermodynamic versus dynamical one. They can be associated with large scale or scale interaction, mesoscale convective events. So how do you modify your analysis if you actually include process-based or phenomena-based additional information? And that may change the probability, perhaps, or reclassify the probability of certain events based on phenomena or mechanism.
Yeah, I agree. I think that would be great to separate per event. So definitely very imperfect, but a first try at sort of trying to not lump too many things together is separating it into these extended seasons, right? So that at least in the tropics, arguably it doesn't matter that much which season you are in, because it will always be convective, and then in the two hemispheres, taking sort of extended summer-winter seasons will at least increase the rate of convective events in the local northern summer versus these large-scale events when you look at winter. So that's one very coarse try to separate a little bit between like regimes and seasons. Like a dream I have is to, I don't know that it'll be feasible, but to better, because one of the main issues is that extreme distributions fitted to observations are really, really, really uncertain. First of all, because we have small samples, but also because given that you have small samples, you want to use all the information you have, but that often means that you do include all sorts of different types of events. And we base it on like an arbitrary grid cell, like whatever boundaries. And I think it would be really useful to try and separate events in a certain representative region and base distributions on event types and relative, like climatologically sort of consistent regions, rather than just arbitrary grid cells. And I think it would definitely change outcomes, arguably, and I don't know how true this is, but I did always determine sort of in which season did the annual extreme happen, and you do see that in most regions there is a dominant season in which the annual extreme happens, which then gives me another reason to believe that it might be a somewhat similar process leading to it. But I think that also really depends on the region. Say in the US, like mesoscale convective systems are a big thing that's in Europe maybe not such a big thing. So here you have to think differently than when you look in Europe. I think, yeah, it's something I would love to do, but I haven't gotten around to it. Yeah.
So how are you thinking how your results depend on the model resolution. And like, if you do downscaling, how actually results look like. I think in the grid cell, like from these models, is quite big. And sometimes when we look observations, the resolution and the downscaling change the results and
Yeah.
the probabilities.
Yeah, so in the observations I looked at, I looked at low resolution observation and high resolution observation, but in any case, they also have a different order of operations, and in general, the rain means something else in observations, because it's not an area average, but it's like determined differently. So you always see a large offset between models and observations. One thing that, like the preliminary results I showed for the Mesa Lab data, for this rainy effect, I started looking in that data because I also want to use the high resolution. So these are two 10-member ensembles, low resolution and high resolution. And I think, especially for this intensification of very extreme events, it does make a lot of sense to go to numerical simulations at a higher resolution to better capture these peak intensities. There's a big difference between models and observations, for sure.
Very nice talk. Just a quick clarification question. This might be outside of my own realm of knowledge, but what is the purpose of using a 5-month season compared to 3-4 month seasons within your analysis?
It's mostly because these block maxima, so the GEV framework, it actually only holds truly for infinite block size.
Okay.
So the longer the block size, the better your approximation of the GEV is. And then given that some, JJA is the summer season, but a lot of extreme precipitation events happen in September. So I sort of wanted to both maximize the amount of events I included, but also get closer to a long block size for my statistical assumptions to hold better.
Thank you.
I was thinking, can we use this frame for other type of climate extremes?
Yeah.
Is it possible using GEP or for temperature? Is
Yeah.
it just for precipitation?
No, it's probably it's more fun for temperature because temperature is less noisy. Like you would get maps that are a little bit less noisy than the ones I showed. I'm actually Eric Fischer, so one of my former colleagues in Switzerland, and Vicky Thompson, who is in the Netherlands. They've been looking at a very similar framework for temperature and also looking at these conditional record-breaking events, which are definitely, also for temperature it matters quite a lot, even though variabilities may be smaller. We still see that there can be a large offset between the current record and the true distribution that then gives some more smooth map of where are regions most at risk for record-shattering heat waves. So you can look up, Vicky Thompson have this paper, it's called Regions Most at Risk for Record-Shattering Heat or so. So yeah, it definitely works for other variables.
All right.
Brian and then Lynch.
I've never worked with this GEV distribution, but of course it's very elegant, comes from a limit theorem that, any IID underlying process, et cetera. So it's a beautiful piece of elegant math, but we're never, it's the limit of infinite data that things will have this shape. And we never have that, and it's never quite IID. Vermont's tropical storm population is different than its garden variety mid-latitude storm population, and only have. So when you're fitting this elegant 3-parameter distribution, you have a new outlier. Isn't there kind of an ambiguity or a stiffness whether you adjust your Xi or you adjust your sigma, and which one you do, has all these implications. You fit the dog, and then does that really fit the tail? Does that really constrain the tail? Just working with it as a statistical working distribution, how stiff or weird or ambiguous is it, and how much do you have to regularize your problem, I guess, or whatever they'd say.
It's in observations, it's really super sensitive to the most extreme event. Like I'm really doing the worst thing you could possibly do with GEVs, right? I fit a distribution to a very small sample, and then I go and determine the probability of the most extreme event of that sample.
Yeah.
Which is the most uncertain thing you can do, because if I remove that most extreme event, I'm going to get a completely different distribution.
Yeah.
And are you familiar with the world weather attribution?
Road
These-
weather. No,
These
that's,
like rapid attribution studies by
Yeah.
Freddie Otto and they sort of do the same thing. So they fit distributions to observations and then they determine what was the likelihood of the event that we saw, like the disaster event. How did climate change the likelihood of that event? And they always also do a study of how sensitive is it to whether we include the event in the fit or not.
yeah,
And that makes a difference of like a factor 1,000 sometimes in like
Yeah.
how much more likely it became given climate change. So in observations in small samples, it's extremely sensitive to this most extreme event. And what you will see, yeah, you're right about the different parameters. So the shape parameter is mostly super sensitive to this. When you have say in California, for example, or like sort of the southwest of the US, everything is kind of dry. And then sometimes you have a few like lost super high intensity events, and that'll give you a shape parameter of like 6, which is completely unphysical. It doesn't make any sense.
yeah.
So it's very sensitive to that. In models, it works, in my view, actually surprisingly well, even for maybe 15, 20 members, which is not a massive ensemble, also not small, but then you get pretty robust estimates. Also because you can use this non-stationary framework where you use all the events and you prescribe like a trend, but you use all the years together to fit one non-stationary distribution instead of using only like single year samples.
Right, well, let's thank Iris one more time. And